Okay, welcome everyone. I'm going to talk about security aspects of DRAM in this International Memory Workshop tutorial. Thank you for inviting me to give this tutorial. I've attended IMW multiple times and given a tutorial and invited talk before. It would have been a pleasure to be in Dresden, the beautiful city, and be with you at the conference. But unfortunately, my travel schedule is conflicted and I have to deliver this talk offline. I'll talk about the story of RowHammer, which probably many of you are familiar with, but I will cover a lot of interesting topics. There are many more slides than we have time for, but these slides are available to you, and I'm happy to take any questions after the talk or at any time. You can email me at this email address. I will start with something that I use to motivate RowHammer to essentially my students. Basically, we look at this bridge. This bridge doesn't exist anymore because a bit flip happened on this bridge, and this bridge essentially became a security, safety, reliability problem. And modern bit flips in memory are like this as well. They affect our critical infrastructure. And I would argue that computing is a much more critical infrastructure today than bridges. Human beings have been building bridges for thousands of years, and bit flips like this clearly affect our safety, reliability, and security. But with computers that are being used in all aspects of our lives, including safety critical, security critical aspects like self-driving cars, for example, we need to be a lot more concerned about these bit flips that could be either erroneously or maliciously generated. I give this example to my students as well, saying that these people are constructing a city, San Francisco, and they're sitting on this rod and they're very happy. But if a bit flip happens in this rod, they will not be happy in the next moment. And I think of security as preventing unforeseen consequences, and bit flips can lead to unforeseen consequences. Basically, hardware designs, especially reliability issues, especially safety critical hardware can lead to a lot of unforeseen consequences in our lives if we don't put security as a prime concern. So what is RowHammer with this backdrop? Basically, it's the fact that you can predictably induce bit flips in commodity DRAM chips. And at the time we tested the DRAM chips, more than 80% of the tested DRAM chips were vulnerable. I'll give you more recent results that show essentially the same thing, frankly, and maybe more. This is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And as a result, people are writing articles that look like this. I think this is exciting from a hardware person's perspective. Forget software. Now hackers are exploiting physics. And this is really a very good high-level characterization of RowHammer. There are physical problems that exist in DRAM chips, and they manifest themselves at bit flips that can be predictably induced. As a result, a security vulnerability ensues. So these sort of reliability issues and technology scaling issues were the focus of my first International Memory Workshop invited talk and attendance in 2013. I'd recommend you take a look at it if you're interested in our argument at that point in time. At that time, we were working on RowHammer, but we hadn't published RowHammer, but we were also working on many different main memory scaling, specifically DRAM and flash scaling issues. I will give you the perspective of DRAM and mention flash briefly. But basically, DRAM is a very common memory technology, clearly. It's used in almost all computing devices. It stores charge in a capacitor, it's charge-based memory. For it to operate correctly, the capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time. As you reduce the size of a DRAM cell, the sizes of both of these structures and other structures also reduce. As a result, the reliability properties, both of these properties become much more difficult to maintain, and DRAM cell becomes much more vulnerable to different types of noise inside the system. We're going to talk about a particular type of noise, but there are many other kinds of noises. And because of these noises, as memory scales to smaller, denser technology nodes, it becomes unreliable. This is data from a paper that we did with Facebook in 2015. The takeaway is that the chip density that's employed in the servers has a high positive correlation with the server failure rate. As chip density increases, server failure rate increases. Why? Denser chips are less reliable because cells are closer to each other and cells are also smaller. And there's a lot of interference between the cells. As a result, there are many error mechanisms that exacerbate in these denser technology nodes. And as a result, servers fail more often. I'd recommend you take a look at this paper if you're interested in more field data based on many servers that we studied at Facebook. Okay, we also wanted to do these studies at a small scale, FPGA-based infrastructures essentially, where we can actually test the DRAM chips and understand these failure mechanisms much better. Because at a data center scale, if you're looking at millions of computers and millions of memory, then it's very hard to control things, because you're not controlling things. Workloads are running in a production data center. Here we wanted to control things, and we wanted to understand different reliability and technology scaling issues of DRAM. So we did a lot of testing. The reason we built this infrastructure was to study the retention time issues of DRAM. But later we studied RowHammer and a lot of latency issues and a lot of voltage issues, a lot of interesting things, as I will mention in a little bit. And this is the infrastructure that was more, let's say, sophisticated, where we studied RowHammer in a more comprehensive way. And we released this infrastructure in 2017 called SoftMC. That's a variant of this infrastructure, and this is relatively easily programmable. We support it. It's openly available. You just need to provide the FPGA so that you can do memory testing in a reliable manner. And this is the paper that is associated with it, if you're interested. And we'd be happy to support any research on this topic. It's been used by industry and academia in multiple studies. Okay, what kind of things did we study with this infrastructure? I'll give you why we built this infrastructure. The main reason was actually to study data retention issues. And data retention is a big problem in DRAM. Basically, DRAM cells have to be refreshed frequently, periodically, every 64 milliseconds, increasingly every 32 milliseconds or 16 milliseconds today at high temperatures especially. And this is a huge bottleneck in terms of system performance energy. And we wanted to get rid of these refresh operations as much as possible. And we wanted to understand the data retention characteristics in DRAM. Because of manufacturing process variation, retention characteristics in DRAM look like this. Basically, most of the cells do not need to be refreshed very often as it's required by the data sheets, for example. Most of the cells can be refreshed at a 4x smaller rate. As a result, you can get rid of 75% of the refreshes if you understand this data retention time profile that looks like this. And we actually validated this data retention time profile with our infrastructure. But of course, exploiting this is not easy because data retention is very much location dependent. You need to understand which locations have which data retention times. It's dependent on the stored values of the cell as well as the cells surrounding it. It's also dependent on quantum-like effects like the variable retention time, which is well documented, but it's becoming much worse in smaller technology nodes, as we show in our papers. Now, I'm not going to bore you with a lot of the research. I think it's quite exciting research, actually, that talks about DRAM data retention times. This is our first experimental study and how to reduce the refresh rates of modern DRAM. But there's a lot of work that we have done where we analyzed a lot of different things like variable retention time, data pattern dependence, and understanding exploiting current memory content, and understanding LPDDR4 devices and profiling in an aggressive way to understand the data retention times. And more recently, we're understanding the on-die error correction mechanisms that are put into the DRAM chips and how to actually model them better so that you can develop better mechanisms that can fix the uncorrectable errors that happen in DRAM. Now, I went through this very fast, but this is what I wanted to show you, to show that the infrastructure that we built enabled us to study all of these interesting questions related to data retention, error correction, DRAM, etc. And if you're really interested in this, we have many lectures related to this, but this is one lecture we have in our classes that you can watch freely available online, as you can see. So that's enabled by the infrastructure. While we were doing these studies, we actually had a separate infrastructure on flash memory where we actually tested a lot of SSDs as well. And with SSDs, we also looked at many different error mechanisms. One of the error mechanisms was redisturbance errors. I'm going to show you that infrastructure's picture later. And we said that, oh, why don't we actually look at this redisturbance errors also in DRAM? And that enabled us to investigate RowHammer, essentially, in this ISCA 2014 paper that was co-authored together with Intel. But we actually started the research in 2012, early 2012. And again, as I said, we found out that one can predictably induce errors in most DRAM memory chips. And that's the RowHammer phenomenon. As we discussed, I've already given you these slides. I'm going to skip some of these slides because you have this in your packet, but maybe you can take a look at it as a reference later. So what is RowHammer? Essentially, it's a DRAM read disturbance error mechanism. Whenever you read a row in DRAM, memory row in DRAM, you need to apply high voltage to it. Whenever you need to read some other row, you need to apply low voltage to the activated row and activate another row. This is called a pre-charge operation in DRAM, applying low voltage and closing the row. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge repeatedly to a single given row, because of the perturbations that you cause and electrical interference that this operation, this hammering operation has with other cells around it. In DRAM chips, in many DRAM chips, we found out that some cells in physically adjacent rows flip. Basically, they lose their charge. They become one. They turn from 1 to 0, 0 to 1, depending on the encoding. Clearly, this should not happen because you were not even writing to memory. No value should change in memory, let alone values that are completely independent of the row that we're dealing with. So basically, we call this hammer row, we call it the victim rows, and we basically showed that more than 80% of the chips that we tested that were manufactured by three major manufacturers, these are the three major manufacturers in DRAM, as you probably know who they are vulnerable. And this is really a scaling problem because the first chip that exhibited this error mechanism was manufactured in 2010. And all of the chips that were manufactured in 2012 and 2013 were vulnerable to this effect. Older chips were not vulnerable because we could not induce enough activations within a refresh interval to actually cause these bit flips. Now, if you cannot induce enough activations to cause a bit flip within a refresh interval, a refresh comes, refreshes the cell. Even though you may have leaked charge, you didn't leak enough charge, and the cells get refreshed. As a result, you don't cause this disturbance error, let's say. But later, in 2010, 2011, 2012, 2013, the number as the cells became smaller and as the cells became denser and the charge became smaller in the cells, these noise effects became increased. The number of activations you could induce, you had to induce to actually cause a bit flip reduced significantly. And we were able to do that within a refresh interval. In our paper, we mentioned the number 139,000 for single-sided hammering, for example. So clearly this should not happen. Why is this happening? Cells are too close to each other. They're not electrically isolated from each other. As a result, this is basically due to cell-to-cell coupling and interference. When we activate a row, an adjacent row gets slightly activated as well. You can think of it that way at a high level. And vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer, it happens enough times before the cells get refreshed, charge in such cells gets drained and you lose data basically. And this has enormous implications in upper levels of the transformation hierarchy, as you can see over here. Basically, you get a bit flip at the device level that really affects the user, algorithms, programming languages, runtime system, the memory isolation mechanisms, as we will discuss. Basically, one can write a user level program that looks like this. And we actually open source this program with our paper, which basically selects addresses X and Y such that they're in two different rows in the same bank, and basically hammers them, bypasses the caches of the CPU, bypasses the row buffer of DRAM. And as a result, you keep hammering X and Y. And if the chip is vulnerable, you'll get bit flips. Now, we also observed that if X and Y sandwich one single row in between them, you get even more bit flips. Later works exploited this as double-sided RowHammer. So actually the numbers, the error rates that I've shown you is much larger if you do this double-sided RowHammer, if you choose X and Y carefully such that you sandwich one row in between them. And we showed in our original work that Intel and AMD systems, we observe real errors, but there's nothing special about Intel and AMD. As long as you can access memory fast enough within a refresh interval, you can get these errors. So essentially all memory controllers are able to do that today. And this is a real reliability and security issue. Clearly, this is a reliability issue, but it's also a security issue because it breaks memory isolation. When we wrote the paper, the first sentence was, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I think we said this, and I believe that this is actually fundamental. If you break memory isolation, if you're able to basically modify some other row's data, somebody else's data, that breaks memory isolation, then you can actually cause errors in any part of the system, in some other application, some other user's data, in a safety critical, security critical page. And as we will see later, people exploited this for many, many different interesting security attacks. For example, the first folks who picked up on this was Google Project Zero folks. They basically were able to write a program that would take over the Linux kernel, become root in Linux kernel essentially. Basically, you can bypass all kinds of privilege levels this way. And this is directly copied and pasted from their blog post. They also have a black hat presentation, which I would recommend you to study if you're interested. I'm not going to read this in detail, but they basically created an attack where a user level process can induce RowHammer bit flips. And it could gain kernel privilege because it's a very special security engineering attack. It's a beautiful attack, actually. It was able to induce bit flips in its page table entries, which provide protection, memory protection to the operating system. These are privileged entries in memory that belong to the operating system. And the operating system sets the privilege level of a process and basically decides whether a process can read or write to a page. And if you can induce the bit flips in the right places in your page table entry, you can gain write access to your own page table such that as a user level process, you can set these bits saying that I can write to anywhere in memory. And once you can write to anywhere in memory by modifying your page table, you can basically take over every data in memory, take over the entire system because you know the structure of the system essentially. And this is a beautiful attack. And later, this work, our work became known as the RowHammer work, let's say, and hackers, say famous hackers on the internet say things like this. Basically, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. Essentially, this is a nice description of a disturbance error. Fundamentally, this is a disturbance error, and I think people at IMW are very familiar with disturbance errors. The difference with disturbance errors and DRAM is they're directly exposed to the programming language, operating system, application. As a result, we're having a lot of trouble with these security issues that are caused by these disturbance errors. It's very different from disturbance errors in flash memory, for example, where you can prevent these errors, fix these errors at the French translation layer using heavy error correction codes. But DRAM doesn't operate that way today. Okay, so there are many other works in the security community that basically talk about how you take advantage of these bit flips. I will not go into a lot of detail over here, but I will point you to these works. These are fascinating works. For example, as early as 2016, these folks showed that they can gain unrestricted access to systems of website visitors by doing these attacks through JavaScript. These folks showed that you could do these attacks on an Android phone. You can actually download the app and they can gain control of the smartphone deterministically. Beautiful mechanisms. These folks show that you can accelerate these RowHammer attacks using GPUs because GPUs can access memory a lot, very fast with high throughput. These folks show that you could actually take over a remote machine in a data center through the RDMA, Remote Direct Memory Access Interface. These folks show essentially the same thing. These folks show that you can break confidentiality. Even if you may not be able to take over a system for whatever reason, you can read somebody else's data, private data, by breaking confidentiality, by breaking isolation again. Right. And more recently, these folks show that neural networks are heavily vulnerable to these RowHammer bit flip attacks. For example, a neural network that accelerator or GPU or CPU, whatever you use, may have a very nice accuracy, like more than 90%. But if someone targets you with these bit flip attacks due to RowHammer, your accuracy may go down to 10%. Essentially, a neural network that's used for pedestrian detection may become useless, even though before it was useful, if someone launched a RowHammer attack or if someone causes reliability issues that lead to this accuracy loss. And I think this is fascinating and it's unfortunate. And there are other works that I'm not going to talk about. And maybe other security implications exist, like you become tired of your computers and you start breaking them like that. So if you're interested in a lot of the studies on RowHammer, we wrote a retrospective on this topic in TCAD in 2019. I'd refer you to that. It covers a lot of works on many different communities, including device level, circuit level, architecture level, system security level, and also more general communities as well. So this is an overview of the work. What this doesn't cover is the work that was done later, meaning 2020, 21, 22, which I'm going to talk about soon. But before we go into it, let's talk about understanding RowHammer. This was our first paper that was published in ISCA 2014. And we did a lot of studies on 129 DRAM modules manufactured between 2008 and 14. And these are our major conclusions, basically. Most modules are at risk. We talked about that. This is a technology scaling problem. Error is correlated with charge loss. And aggressor and victims cells are actually, victim rows are adjacent to each other. Some of them don't look adjacent to each other because there's some internal row address remapping that happens in DRAM chips due to fault tolerance purposes. And this is not exposed to the memory controller. As a result, solutions that are implemented in the memory controller need to think about the adjacency of a hammered row and a victim row, because memory controller doesn't know the physical adjacency of these rows, whereas DRAM chip DRAM chip designers know that information. This is the access interval. Basically, if you access memory less frequently, meaning increase the access interval to the aggressor, increase the interval between two activates, you reduce the errors. This is clearly expected because you're hammering less frequently, as you can see. But if you increase it, you're hammering more frequently and the errors increase. So one way of solving the problem is to increase the access interval significantly, but that's very disruptive for performance. We don't want to dictate a long access interval between two consecutive activates. As we will see, this is not going to be viable because technology scaling is not working well for RowHammer. The fewer number of activates lead to RowHammer bit flips today, basically. Refresh interval, which is actually a very insignificant lever. When we tested the refresh interval, was nominal refresh interval was 64 milliseconds. As you reduce the refresh interval, basically bit flips reduce because you're more frequently refreshing the memory. And at some point, you get rid of bit flips. But to be able to get rid of bit flips and every single chip that we tested from every single manufacturer, you need to increase the refresh rate by 7x, which is not a great idea, as you can see. But unfortunately, this is the major lever that was adopted by industry initially because we don't have configurable programmable memory controllers. As a result, people are going to increase the refresh rate, as we will see. This is another example, data pattern. Data pattern matters because it affects the coupling between the cells. As a result, the data pattern on the right over here leads to an order of magnitude more errors than the data pattern on the left. This is very similar to refresh, for example, retention times. Okay, we also showed that retention weak cells and RowHammer victim cells actually don't have any overlap because these are very different failure mechanisms. Errors are repeatable. Basically, this leads to a security problem. Once a cell can be hammered, it can be hammered again. So you can actually profile which cells are vulnerable and actually take advantage of this in your security attack. You get as many as 4 errors per cache line. So error correcting codes, actually simple error correcting codes, do not prevent RowHammer bit flips, at least all of them. And cells are affected by 2 aggressors on either side, so you can have double-sided tamper. And if you're interested in more results, our original paper has a lot more results, and I'd refer you to that. And more recently, we showed that RowHammer is getting worse. I'm going to talk about this. So there's more understanding that we developed, and even more understanding we developed more recently, where we talked about new RowHammer dimensions like temperature, voltage, etc. And this is the voltage that's going to appear soon in DSM. Before I go into these recent studies, let's talk about RowHammer solutions. Basically, if you discover a vulnerability like this, there are 2 solutions that you need to think about. One is immediate. How do you protect the vulnerable DRAM chips that are out in the field that people are using? Clearly, there are limited possibilities here because there is not enough configurability and patchability in the hardware that we have today. Certainly not in DRAM and very little in memory controllers. But longer-term solutions can be more aggressive. They can protect future DRAM chips with a wider range of protection mechanisms. Our original paper proposes 7 solutions, both types. And Para, as I will discuss, is proposed as the best solution. It's already employed in the field, variants of it at least. But I think going forward, we need to think about even better solutions because this is not scaling very well. So these are some potential solutions, as we discussed: refreshing frequently, making better DRAM chips that are better isolating these aggressor and victim rows. Cost is a bigger problem over here. Refreshing frequently is a heavy-handed thing to do. Sophisticated ECC is a heavy-handed thing to do also because ECC, error correcting codes, are very good at correcting random errors that you do not know the cause of, like soft errors. But unfortunately, I don't believe that they're a good fit for RowHammer type of errors that you know the cause exactly of, because they become extremely inefficient in correcting RowHammer type of errors that lead to a lot of bit flips. And access counter-based mechanisms keep track of access counts to different rows and try to throttle rows that have been accessed very frequently, for example, or try to refresh victim rows of the rows that have been accessed very frequently. We're going to talk about that later. But let's talk about the solutions industry adopted. Clearly, in the field, you need to protect the chips. This is an adopted solution by Apple. Basically, Apple increased the memory refresh rates, and they were nice enough to credit our work because of this, basically. They basically said they did this because of RowHammer. They didn't tell by how much. Probably they increased by 2x, which is not enough to get rid of all of the RowHammer bit flips, but it closes the vulnerability element. As our paper showed, you need to increase the bit flips, increase the refresh rate by 7x to get rid of all of the bit flips, which is a lot. So clearly, increasing the refresh rate is not good because it increases the energy consumption of the system as well as reduces the performance of the system. But people are doing this so that they can protect against RowHammer. And we ideally don't want to increase the refresh rate of a system, make one technology scaling problem worse to fix another technology scaling problem, because retention and refresh are technology scaling problems in DRAM. RowHammer is another technology scaling problem. You don't want to make one technology scaling problem worse to fix another technology scaling problem. So we really want to get rid of refresh still, in my opinion. Okay, as much as possible. So our solution was more probabilistic. It was actually very low cost. The idea is to implement this in the memory controller, but it could be implemented in DRAM chip as well. After closing a row, the memory controller activates one or both of the neighbors of the row with very low probability. And you can adjust the probability depending on your, let's say, paranoia. And if you have a probability 5 out of 1,000 times, you get very good reliability guarantee. That's better than hard disks. And this is low power, low performance overhead, as we show in the paper. It's stateless, low cost, and low complexity. And we said that this is an effective solution, especially at the RowHammer counts, the activation counts that you need to induce RowHammer flips at the time. So you can implement this in the DRAM chip. Actually, a lot of manufacturers use variants of our solution internally because we reverse engineered a lot of the solutions, as I will discuss later. You need some slack in the memory timing and refresh parameters, and manufacturers are using that slack today. In DDR5, there's the RFM command, which actually increases the slack a little bit by putting more burden on the memory controller, let's say. You can also implement this in the memory controller by having better coordination between the memory controller and DRAM. Basically, memory controller should know which rows are physically adjacent. It can predict that physically, like logically adjacent rows are also physically adjacent. And most of the time it'll be correct, but there will be some of the time it won't be correct. So it will not be able to get rid of all of the RowHammer bit flips without cooperation from the DRAM chips and DRAM manufacturers. And that's the unfortunate state of DRAM interfaces today, in my opinion. We don't have enough cooperation between the memory controller and DRAM to fix critical reliability issues like this. We're going to get back to this. So our solution argued for this cooperation, and it was implemented in the PTRR mechanism by Intel. This is one of the screenshots of the BIOS of Intel systems. So you can pick your RowHammer solution, either hardware RowHammer protection or double the refresh rate. And if you pick hardware RowHammer protection, there's a probability of refreshing at every some number of activations, and you can basically pick one out of 2048 times, for example. So you can pick your choice in terms of how reliable and secure you want to be against RowHammer with this sort of mechanism. This is a little bit different from what we envisioned, because we envisioned this as a dynamic mechanism as opposed to configurable at the BIOS level, but this is a step in the right direction. It's making the memory controller more intelligent to solve the problem. Okay, so if you're interested in other solutions, the paper has a lot more details, but I think one major takeaway is we want intelligent controllers to solve issues like this so that we can become more secure, safe, reliable, and fix the technology scaling problems. This is true for DRAM retention times as well. If you want to fix the refresh problem, you really need to have intelligent controls that understand the different characteristics of the DRAM cells and refresh the cells based on those different characteristics. And this is the flash infrastructure that I mentioned earlier. So we know how to design intelligent controllers. Actually, NAND flash memory is a memory that has a lot of reliability and scaling issues, and the controller makes it work. The flash translation layer makes this work. And basically, we had FPGA-based memory controllers, and we did a lot of work in this area. And it's fascinating what's employed in these controllers. This talks about the state of the art in flash memory controllers. If you're interested, you can take a look at this Proceedings of the IEEE paper that we published a few years ago. Okay, there's more on RowHammer basics. And if you're interested, I would recommend you take a look at our lectures as well as the paper. I'm now going to talk about more recent studies. But before more recent studies, we actually also wrote other papers that summarize the problem. If you're interested in the summary of the problem, you can take a look at this paper. And as I said, if you're interested in a large overview, this paper gives that large overview. Now, let me talk about what happened in 2020, 2022 timeframe, because it's been very exciting. Basically, first of all, we revisited RowHammer as the same group who looked at the fundamentals of RowHammer to begin with. And this is the paper that we revisited in 2020. These are the key takeaways. Essentially, newer DRAM chips are much more vulnerable to RowHammer across from our analysis of more than 1,500 DRAM chips from 3 different standards, as well as multiple different generations. Basically, we get more RowHammer bit flips. They're happening earlier, meaning with fewer activations. They're new chips whose weakest cells fail after only 4,800 hammers. And chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. Basically, this disturbance effect is becoming stronger, essentially. And existing mitigation mechanisms are unfortunately not effective at future technology nodes. For example, if the hammer count becomes 1,000, 500, 200, 100, then it becomes existing mitigation mechanisms like probabilistic adjacent row activation becomes very high overhead. And the paper has a lot more detail on this. Increasing the refresh rate across the board becomes unreasonable, basically completely unreasonable, because your performance drop reduces by 10x, for example, by increasing the refresh rate. So we need to think about new mitigation mechanisms going into the future. So let me give you an example of the studies that we did. Basically, we tested DDR3, DDR4, LPDDR4 chips. We have different infrastructures for these. And these are example DRAM chips. This is a busy slide, but it basically talks about what are the DRAM chips from 3 major manufacturers. And we have different technology generations, as you can see. Let me give you one result over here. Basically, this result shows from 3 major manufacturers that as you go from an older DDR4 generation to a newer DDR4 generation, RowHammer bit flip rates across the board increase for all manufacturers, as well as the hammer count, the activation count that you need to get to first bit flip reduces because the curve shifts up and left, as you can see over here. And I think I've already said this basically. Basically, RowHammer vulnerability becomes worse with each technology generation. This is another graph, again, another busy one. But basically, this shows that newer chips from each manufacturer are more vulnerable to RowHammer. On the y-axis, you have the hammer count needed to induce the first bit flip. On the x-axis, you have different technology nodes. And each technology node, you go from left to right, you scale to a newer technology node, let's say. Different types of DRAM also. Sorry, I said technology nodes. But basically, the number of hammers that you need to induce to get to the first flip is reducing across the board, across manufacturers. And these are the exact numbers. I'm not going to talk about these because we don't have time, but you can read them in your slides, sir. So basically, this paper proved that RowHammer at the device level is getting much worse. And what should we do about it? If you're interested, there's a lot more longer explanation of these results in this particular lecture. So, but what happened at the same time was DRAM manufacturers said that they built RowHammer-free chips. They basically, multiple manufacturers claimed publicly that their chips were RowHammer-free. but they didn't tell the public how. So we basically took up the challenge to check out whether this is true and how do these solutions work basically. And we found out basically these industry adopted solutions that are claimed to be RowHammer free essentially do not work. And this is the trespass paper. Basically, we show that TRR protected DRAM chips. TRR means target row refresh. That's basically the generic name attributed to these RowHammer solutions that are employed by the DRAM manufacturers. We don't know how they work. It's not specified anywhere, but it's advertised as secure. But we showed that they're not secure. Basically, we introduced the many-sided RowHammer attack here. By hammering many rows, not just two, more than two, you can bypass these internal target row refresh mitigations by overflowing proprietary tables that are internal to the DRAM chips that are supposed to detect aggressor rows. Basically, we partially reverse engineer the existing implementations of TRR mechanisms that are implemented in DRAM chips and memory controllers. And we provide an automatic tool that can effectively bypass these mitigations, at least for a significant fraction of the chips and mobile systems. So that's the idea, basically. So what's a many-sided RowHammer attack, hammering pattern? Basically, instead of hammering one row or two rows so that you can actually do a double-sided attack, you can hammer 3 rows, for example, or 4 rows, or 13 rows, or 19 rows. As you can see, different chips are vulnerable at different number of aggressor rows. For example, this chip from DRAM manufacturer C is vulnerable after once you hammer 5 rows. Here you hammer 7 rows. Here you hammer, I don't know, 9 rows. The paper has a lot more detail on the trade-off between hammering more rows and hammering one single row longer, let's say, adding more activations. There's clearly a trade-off over there. But basically, we found out that there are best patterns that can lead to RowHammer bit flips in the presence of these mitigations that are employed by the manufacturers. You can see the best pattern over here. Some chips you need 19-sided hammers, and you can see the bit flip counts that we can induce. Even a single bit flip can be exploited as a security vulnerability, basically. But we get, in many chips, we get thousands of bit flips, as you can see over here. Okay, and we actually showed that you can take over real mobile phones, and these are marked in check marks over here. And the paper is a lot more detailed, and the time to attack is actually relatively quick, as you can see over here. These are different types of RowHammer attacks, and time to attack is in terms of seconds or minutes sometimes. Okay, basically these are our key results. A significant fraction of the tested DDR4 modules are vulnerable, even though they're claimed to be RowHammer free. And a significant fraction of the mobile phones that use LPDDR modules are vulnerable. And these results are scratching the surface. Basically, our tool was not really exhaustive. This was just to demonstrate a proof of concept. And there's still a lot of room for uncovering more vulnerable chips and phones. And we said that, and then we started working on truly uncovering the underlying implementations, basically. But the takeaway is that RowHammer is still an open problem. Security by obscurity is likely not a good solution. It's better to be open about your security solution and say, here's how my security solution works, attack it, and let's make it stronger together. I think that kind of mindset in memory industry can significantly improve the security, safety, and reliability of our systems going forward. And we argue that in a recent position paper that I will mention. And this is our detailed lecture on trespass. I have a lot more slides and descriptions in this particular lecture. Okay, so we later also looked into how to guarantee that a chip is RowHammer free by exhaustive testing, by figuring out how to do that in real systems. And this is a very difficult problem. I'm not going to talk about this in detail. I don't think there is a good solution to this completely because RowHammer depends on many things, access patterns, etc. But this paper that we wrote with Microsoft talks about it, and it has a lot of interesting data. If you're interested, take a look at it. As I said, we started uncovering TRR mechanisms almost completely, and this paper essentially uncovers them completely. Basically, the reason is to study the security properties of these mechanisms. To be able to do this, we developed a new methodology that leverages data retention failures to uncover the inner workings of TRR and study its security. Basically, we reverse engineer which rows have what retention times, and we reverse engineer the chips and the mechanisms enough so that we figure out whether a refresh is performed due to a periodic refresh induced by the memory controller, or whether a refresh to a row is performed due to an internal refresh or internal DRAM refresh to overcome RowHammer. Because existing DRAM chips do internal refreshes called TRR, target row refresh, to overcome RowHammer. These are not exposed normally, but we figured out a way to actually distinguish between which refreshes are internal and which refreshes are external induced by the memory controller. And as a result, we were able to come up with new RowHammer access patterns that could overcome the internal protections. And all 45 DRAM modules that we test from 3 major vendors are vulnerable. And more than 99.9% of rows in a DRAM bank experience at least one RowHammer bit flip. And we find up to 7 RowHammer bit flips in an 8-byte data bird, making ECC essentially completely useless. And we conclude that TRR existing mechanisms do not provide security against RowHammer. And hopefully our methodology, which we will open source soon, will facilitate the development of new RowHammer attacks and more secure RowHammer protection mechanisms. Okay, I'm not going to go into the details of these slides. These are here for your benefit. You can take a look at them. We developed this new infrastructure, which we are going to release also. This is the DDR4 infrastructure. And basically, you can circumvent TRR. This is an interesting table. Basically, this is based on our reverse engineering. You can see that these are different vendors, and they have different aggressor detection mechanisms. They either count the number of hammers, for example. They either do sampling, random sampling, for example. They have a mix. The capacity of the tables are different, as you can see. Some of them are per bank, some of them are per rank. And the different refresh ratios, at what frequency do they issue these RowHammer refreshes compared to periodic refreshes are also different. And the number of neighbors that are refreshed compared to an aggressor row are also different. And you can see that we're successful in our bit flips because most of the rows are vulnerable, and we get a lot of bit flips per RowHammer, as you can see. Okay, I've already given you these results, and I believe with more time spent, you can actually find that chips are even more vulnerable than we have discovered. We had limited time to actually show this and write the paper. But the key is ECC error correcting codes as today do not work, because you can induce as many as 7 and many times more than 3 bit flips, and sected ECC doesn't work. And if you're interested, the paper has a lot more detail, and we also have lectures on it. You can find the links to the lectures in these talk videos over here. Okay, let me talk a little bit about some other new RowHammer characteristics that we discovered. This is another Micro 2021 paper, which was published in October 2021, where we looked at 3 major properties: temperature, aggressor row active time, and victim DRAM cell's physical location, to understand how RowHammer vulnerability changes based on these, so that we can have more effective and efficient attacks as well as defenses. Again, these are our infrastructures, and these are the chips we tested from 4 major manufacturers. The 4th one is a bit small, but it's good to see that actually all manufacturers have similar trends as we discovered. So I'll give you the major takeaways. Basically, we have more than 270 chips, and we have 6 major takeaways and more than that of level observations. We find that RowHammer bit flips is more likely to occur in a bounded range of temperature. Different cells have different vulnerability temperatures, basically. And if you really want to exercise RowHammer, you need to do exhaustive testing across a very different temperature range to really understand this. If the aggressor row is active for a longer time, you get more RowHammer bit flips. This is counterintuitive, but it's an interesting effect. It's also called the Ras-Klauber effect, for example. In certain physical regions of the DRAM module under attack, you get more RowHammer bit flips. Basically, there's a lot of manufacturing variation. And as a result, different regions of the DRAM module is significantly differently vulnerable. And these observations can be used to craft more effective attacks and design more effective and efficient defenses. Let me give you some example attack improvements. For example, existing attacks activate aggressor rows as frequently as possible. But our paper shows that this is not the best approach to induce bit flips quickly or more bit flips. Essentially, if you keep aggressor rows active for a longer time and still hammer the same number of times, you get 36% reduction in the number of activations you need to do to get to the first RowHammer bit flip, which is interesting. And if the defense mechanisms do not take into account this reduction because they're tuned for a particular RowHammer vulnerability value, activation count, let's say, then they may actually be insecure at that point. So these are the implications of this deeper understanding of RowHammer, as you can see. So in terms of spatial variation, we find out that the RowHammer vulnerability varies significantly across DRAM rows and columns due to design-induced as well as manufacturing process variation. And the distribution of the minimum activation count to observe bit flips exhibits a diverse set of values in a subarray, in a DRAM subarray. But within the same DRAM module, similar values across subarrays. So there's actually potential for improvement and understanding as well. I'm not going to go through this in detail, but basically this picture shows that the RowHammer vulnerability varies significantly across DRAM rows. You can see the huge difference between the minimum activation count that you need to induce to get to the first bit flip across different DRAM modules. And you can see that DRAM rows are sorted in terms of their vulnerability over here. These are the most vulnerable rows over here in a different DRAM chip. And clearly there's vulnerability across the different DRAM chips as well. And this is true for 4 different manufacturers, as you can see. There's not much difference between manufacturers, except the exact numbers differ a little bit. Okay, there's spatial variation across the rows, as you can see over here. A small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. And a small, again, different columns are differently vulnerable. Certain columns are significantly more vulnerable to RowHammer than other columns. Again, this is because of manufacturing variation. And you can leverage this basically. If you know which cells are vulnerable, how much to RowHammer, and our understanding is that a small fraction of cells are a lot more vulnerable than a greater fraction of DRAM cells, as you can see in this picture. You can significantly improve existing defenses. The aggressiveness can be reduced for cells that are less vulnerable and increased for cells that are more vulnerable, and can develop much more efficient RowHammer defenses this way. Again, similarly, you can leverage the variation of vulnerability in terms of temperature. You can disable some rows based on the temperature. This is not easy, I would say, because this requires a lot of testing, clearly, of the chip and understanding the vulnerability, but it can lead to more efficient defenses. The jury is still out there. Needs to be more work on this. There's a lot more analysis in the paper, and we're doing more analyses currently. If you're interested, I'm happy to talk about this, and you can find more information about the paper as well as talk videos, as you can see over here. So there's more RowHammer analysis that we're right now doing, and this is going to appear in DSN in 2022, where we analyze RowHammer with respect to the word line voltage. And we find out that basically voltage swing on a DRAM row's word line causes RowHammer, and there's no prior study on the impact of voltage. And we study this effect rigorously. And we find out that RowHammer vulnerability can be reduced via voltage scale. It will not solve the RowHammer completely, but it can reduce the vulnerability. And for that, I would recommend you take a look at our upcoming paper. It's critical to develop new RowHammer solutions. I'm going to talk about solution space a little bit right now. Basically, clearly more robust DRAM chips and our error correcting codes can be solutions, but I will ignore these because these are very costly solutions in my opinion. Increased refresh rate can be a solution, but again, this is a very costly solution today. Physical isolation is a software level solution. Can you isolate victim rows from aggressor rows? This is very difficult to do in practice, and it leads to huge memory waste, essentially, because you need to have isolation rows where you cannot put anything, essentially, and because you need to have large enough distance. So it wastes, let's say, 75%, 80%, 90% of your memory, depending on your RowHammer vulnerability. Reactive refreshes, you identify the aggressor rows somehow and refresh victim rows, potential victim rows. This is employed by industry today, but it, again, is not secure enough. You could make it secure enough, but overheads may increase. Proactive throttling is you identify the aggressor rows somehow and throttle the activations to it so that you don't actually activate it more to cause RowHammer. I think these solutions are actually quite interesting to study so that we can get to a better position. And there are also probabilistic solutions that can employ partially increased refresh rate, like reactive refresh is probabilistic. It could be deterministic as well. But of course, the solution space covers cost, power, performance, and complexity concerns. And we need to come up with a very good, let's say, trade-off so that we can actually completely solve RowHammer. I do not think we're there yet at this point. But let me cover the BlockHammer solution that we introduced recently. Basically, there are two key challenges any solution needs to tackle. One is scalability with worsening RowHammer vulnerability, and the other is compatibility with commodity DRAM chips, especially if you're implementing in the memory controller. And our goal was to prevent RowHammer efficiently and scalability without knowing the internals of DRAM from a memory controller perspective, basically. This solution can be employed inside DRAM also. Our goal was to show that you could do it in the memory controller, but inside DRAM, you could also do this, frankly. But inside DRAM, of course, the cost trade-offs are different, right? And the idea is to selectively throttle memory accesses that may potentially cause RowHammer victims. So there are two components to our mechanism. One is row blocker. The other is attack throttler. Row blocker tracks row activation rates using area-efficient Bloom filters. This is actually very nice. You can use Bloom filter hardware so that you can track row activation rates. And the Bloom filter hardware says, oh, you're activating this row too much. So the memory controller blacklists, basically saying that I'm not going to activate this row. I'm going to deny access to this row for some time. That's the throttling of the activations, essentially. And if you do it at the right time, you can securely prevent RowHammer. No row can be activated at a high enough rate to induce bit flips. Now, attack throttler is interesting. Identifies threads that perform a RowHammer attack. It reduces the memory bandwidth usage of these identified threads by throttling them even more. And it greatly reduces their performance degradation and energy waste of a RowHammer attack that a RowHammer attack inflicts on a system. So a RowHammer attack, actually, existing mechanisms can lead to turn a RowHammer attack from a security problem to a performance problem by increasing the refresh rate, for example. Here, we have an opportunity. By identifying which threads are actually causing this, we can actually significantly reduce the burden, performance burden on the system. Sometimes the operating system can deschedule that and examine those threads, for example. And again, this is a busy slide with a lot of results, but basically, when there's no RowHammer attack, the performance and energy overheads are negligible, as you can see, less than 0.6%, which is great. When there is a RowHammer attack, BlockHammer actually improves performance because it takes away the large impact of the hammering thread by throttling it and frees up the memory bandwidth for other threads that are benign, that are not attacking, essentially. Okay, so these are, we also show that you get better hardware area scaling with RowHammer vulnerability compared to other mechanisms. And we have a security proof of this. We address many-sided attacks as well. And we also have a comprehensive description of 14 mechanisms that represent the 4 mitigation approaches, the RowHammer. I'm not going to go through the details of it, but the paper has a very rigorous analysis of all of these mechanisms over here. And I'd be happy to talk about it if there are questions related to it. But if you're interested, you can study. This is, to my knowledge, the most comprehensive paper that covers many different mechanisms that identifies the upsides and downsides of different approaches that are published in literature or employed by the manufacturers. But the key takeaway is main memory needs intelligent controllers for security, safety, reliability, and scaling, as I mentioned earlier as well. Okay, so this doesn't cover everything about RowHammer in 2020 and 22, but we don't really have time to cover more. Clearly, there are papers that are written in top conferences. For example, IEEE Security and Privacy, the conference, which is a flagship conference of IEEE, had a session on RowHammer, talks about attacks and solutions in 2020, using security. Hot OS, basically OS folks are also thinking about RowHammer, as you can see. Clearly, security folks are thinking a lot. Microarchitecture and architecture folks are thinking a lot. This is happening actually next week, I believe, in San Francisco. Again, the flagship conference of IEEE on security and privacy. And there are 3 RowHammer papers that are coming up, which are quite interesting, I believe. Architecture conferences also have very interesting papers, as you can see, some solution papers, some attack papers, some analysis papers. This is another conference, International Reliability Physics Symposium, that also looked at RowHammer, as you can see this year. And we have an upcoming position paper that talks about being more transparent about reliability characteristics in DRAM systems, such that the memory controller and the DRAM chips can cooperate better to solve issues like RowHammer, as well as retention, as well as latency issues. And I would recommend you take a look at that. We believe that better cooperation between the memory controller and memory can actually solve a lot of these scaling issues much more easily. But this needs to be, of course, discussed across the industry in an open manner, let's say. So there's more to come, I believe. Now, let me take a quick aside to future memory reliability and security challenges, because I've talked about RowHammer, it went very deep, but clearly DRAM is becoming less reliable and more vulnerable. Due to difficulties in technology scaling, other problems may also appear, or they may already be going unnoticed. Some errors may already be slipping into the field. Redisturb errors are examples. Retention errors are other examples. For these reasons, clearly industry introduced ECC, but ECC caused its own problems. And these errors can also pose security vulnerabilities, unfortunately. And it's not just about DRAM. It could be about flash memory, although flash is an advantage because it has FTL built next to it. So it has an intelligent controller already, actually. Emerging memory technologies could cause issues also. Phase change memory, STT-MRAM, RRAM, memristors, racetrack memory, etc. Many memory technologies that are discussed in IMW for decades and this year as well. Clearly, we need to think about these security problems, disturbance problems, noise problems that can lead to safety, security, and reliability issues. I believe with intelligent controllers and memory and controller cooperation and co-design, we can actually fix a lot of these issues, in my opinion. Because intelligent controllers can avoid many failures, enable better scaling. They can be updated, patched in the field much better, especially if they're programmable and reconfigurable. So I believe we need to actually follow 3 major directions, frankly. First, we need to understand the issues. We need to develop methods for vulnerability modeling and discovery, model and predict based on real device data and analysis, understand these vulnerabilities and develop reliable metrics. I don't have time to go over the details of this, but our papers talk about this, especially the RowHammer retrospective paper, for example. If you're interested, you can take a look at it. We want to architect. We want to design principled architectures with security as key concern from the ground up in DRAM and in the memory controller, as well as the entire system. We need to partition the duties across the stack. I don't think we should try to solve every single problem inside the DRAM chip or the flash chip. I mean, flash chip is already not solving every single problem. There's a controller. We cannot give up performance and efficiency. That's important, especially in main memory. And I believe patchability in the field is very important to provide going into future generations of DRAM as well as memory controllers. Of course, design and test is critical. Principled design, automation, and online testing, such that we're not missing anything, is important. And for this, we need to design for security from the ground up. And if we can profile the DRAM chips online once in a while, and if there's profiling support that's provided by the DRAM interface so that we can make this low cost and low overhead, we can get high coverage and good interaction with system reliability methods. That's what our position paper talks about as well. Okay, that's one of the reasons why we've been doing a lot of studies with DRAM so that we can build these models and understand these vulnerabilities. We've been doing a lot of these studies with Flash as well, so that we could build these models and understand vulnerabilities. So both with planar Flash as well as 3D Flash. And I'd recommend you take a look at our proceedings of the IEEE paper. We also have an invited book chapter in the Inside SSD Drives book that came after this that talks more about 3D NAND, essentially. So let me go back to the picture that I showed you earlier. Essentially, these bit flips are critical in real infrastructure. Real infrastructure meaning bridges, like very heavy infrastructure, I would say. Clearly, these bit flips are unfortunate because they may actually lead to casualties. This is Han River in Korea. This is Minneapolis in 2007. This is Genoa in 2018. So basically, unfortunately, these happen in real life. They don't happen every day, but when they happen, they're deadly. They could be deadly, let's say. So we want to prevent these bit flips also. And these infrastructures, these heavy-duty infrastructures have a problem. They're not patchable. They're too heavy, basically. But in the computing domain, both inside the memory controllers as well as the DRAM, as well as the operating system, entire system, we are much softer, meaning we can patch things better. If we're more intelligent about it, we can add in-field patchability. We can avoid such failures. And that brings me back to the invited talk that I gave at International Memory Workshop 9 years ago, where I talked about these issues and talked about essentially this sort of memory controller cooperation. And we're not the only ones talking about it. Industry, Intel and Samsung actually wrote this nice paper in the Memory Forum in 2014, where they talked about DRAM process scaling challenges. I'm not going to read through these, but refresh and variable retention time, things that we discussed earlier, come back, as you can see. They don't talk about RowHammer because that was not exposed yet, let's say. And they basically argued that you need to co-architect controllers and DRAM so that you can solve issues like this. And I believe that this is really critical to do going forward. Now, let me give you my final thoughts on RowHammer, and then we will conclude. Basically, this is a beautiful paper from IEEE Security and Privacy in 2003. This is 11 years before RowHammer. These folks from Princeton University showed that you can induce bit flips in existing systems by physically increasing the temperature in the DRAM. And these bit flips, you can take advantage of these bit flips to take over the Java virtual machine or the .NET virtual machine using very clever security attacks, let's say. I'm not going to talk about these security attacks, but you can read the paper. The interesting thing is they injected these faults using a lamp that looks like this. You can see this lamp. This lamp heats up the DRAM in the system and causes a lot of errors. And they basically take over the system, take over the virtual machine because of these errors. This is a very interesting paper because Google's later work on RowHammer took advantage of this work, let's say. But this is ahead of its time. Clearly, everybody said, oh, if you have you need to have physical access to the system to induce these errors. But with RowHammer, we showed that this memory error can be induced by software. You don't need to have physical access. You can just run software. And if the DRAM chips are vulnerable and you can induce these bit flips predictably, then it can take over the system. So basically, RowHammer had created a new mindset that has enabled a renewed interest in hardware security attack research. Now, software people, security people became very, very interested in memory issues, let's say, because real memory chips are vulnerable in a simple and widespread manner, and this causes real security problems. And I think that's a good thing for our industry. Going forward, we need to actually ensure that safety, security, reliability are extremely important because our chips are going to be used in extremely critical conditions. We cannot avoid the problem. We cannot ignore the problem. We basically need to work with the entire ecosystem to solve this problem, in my opinion. And hardware reliability and security connection is now mainstream discourse in the security community and architecture community. There are many new RowHammer attacks, tens of papers in top security and architecture venues, and they're actually diversifying. I believe there's more to come as RowHammer is getting worse, and the solutions do not work currently. There are many new RowHammer solutions, as you can see, as we have discussed. And principled system DRAM co-design, as we argued in our IMW paper and initial RowHammer paper, is, I think, extremely important. I believe there's more to come as well. Most importantly, I think this mindset, a shift of mindset in mainstream security researchers showed that was instigated by the fact that general purpose hardware is fallible in a widespread manner. Its problems are exploitable. And this mindset has enabled many system security researchers to examine hardware in more depth and understand the hardware's inner workings and vulnerabilities. And I believe it's no coincidence that two of the groups that discovered Meltdown and Spectre heavily worked on RowHammer attacks before. And I believe there's more to come in hardware security, including memory security as well. So let me conclude. Memory reliability is clearly reducing, especially with technology scaling. Reliability issues open up new security vulnerabilities. These are very hard to defend against. RowHammer is a prime example. As I said, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. I believe its implications on system security research are tremendous and exciting, as we have been seeing across the field. Bad news is RowHammer is clearly getting worse at the device level, and the industry maybe is not in the right mindset to develop the best solutions, but hopefully they will fix that issue. Good news is we have a lot more to do. We're now fully aware hardware is easily fallible. We're developing both attacks and solutions, and we're developing hopefully principled models, methodologies, and solutions. Most importantly, in my opinion, we need to develop good interfaces and good communication between the controllers and DRAM, such that we can actually fix these issues in an easy and patchable way. Basically work together between the vendors of different parts of the system as opposed to work against each other. Okay. Again, I will conclude with the survey. I will point you to the survey for a lot of the important works. The survey covers a lot of ground. And I will, if you want to get a full picture, let's say we have detailed lectures on RowHammer that were delivered in fall 2021. And I will acknowledge funding that we have received generously from many companies. Thank you to all of them. Most importantly, I will acknowledge the research that was done by a research group. Many of these works were clearly done by my students collaboratively with me. And you can learn more about them in this link and our newsletter. And if you're interested in a lot more about issues like this and memory issues, memory-centric computing, etc., you can attend our classes, advanced computer architecture classes, as well as early computer architecture classes. All of these are live streamed on YouTube, available for everyone to attend live or later. And we'd be happy to get any feedback from industry, especially about anyone who's attending this talk. Thank you very much. I appreciate your attention, and I'd be happy to take questions in the live session. Thank you.